We have a lot of material today, the geometry and algebra of Euclidean space. So we talked a bit about solving algebraic systems and mentioned briefly that solutions can be thought of as intersections of certain geometric objects. For example, y equals x and y equals 2x plus 1 intersect when x is 2x plus 1, when the y values are equal. And then you have to figure out the x values. They also have to be equal, and they are when x is minus 1, just by subtracting x over and subtracting 1 over. So they intersect at minus 1, uh, giving a unique solution to the system y equals x, y equals 2x plus 1. And there are analogs in higher dimensions, such as two planes generically intersecting in a line, or three in one point. And to talk about lines and planes intersecting, we should learn how to work with them algebraically. Let's talk about coordinates in 2 and 3 dimensions. We can represent coordinates in R2, or more generally Rn, as column vectors xy, or more generally x1 through xn. Writing them in a textbook, we usually write xy and x1 through xn for these column vectors, so they fit better in this text. When we think of column vectors in Rn, we think of them together with some algebraic rules that also have a very nice geometric meaning. The algebraic rules follow from all of the rules of matrices we already learned. Addition of vectors is component-wise. Scalar multiplication is component-wise. And we can't multiply n by 1 with n by 1 vectors using matrix multiplication. Geometrically, we haven't yet talked about what addition and scalar multiplication mean. So let's talk about that now. So in figure 1 below, which we'll get to soon, we see that adding two vectors corresponds geometrically to something called the parallelogram law. So here it is. If I want to add a vector u, which is the magenta vector, and a vector v, which is the green vector, so we think of them both as coming out of the origin, but I could take one and just attach it on the right side where the other one ends, and I get a new vector given by the hypotenuse or diagonal of these uh, two vectors. So u plus v is v plus u from this diagram that you should take a look at. And algebraically, we just add the coordinates. So 3, 1, and 1, 2, we add to get 4, 3. And this really is the point 4, 3 at the very top right of this vector. So the vector is 4, 3. But this isn't new. To compute 3 plus 2, you could think of taking the number 3 and attaching 2 more to it to the right. Right? You start at 3 and then you count 4, 5. Or you can think of 2 plus 3 as something totally different. Take 2 and attach 3 to it. So 2, 3, 4, 5. We still get 5. So real numbers are also vectors. We could think of the same geometry there as well. So that's how we add. And to scale a vector, we just multiply it by a constant c. Geometrically, that means you multiply the length of it by c. We haven't talked about length yet. And if c is negative, then you also flip the direction, and we haven't talked about direction yet. In general, the vector starting at p and ending at q is denoted by pq and is computed with q minus p. So for example, this vector starts at 1, 2 and ends at 4, 3. So this vector v is 4, 3 minus 1, 2, which is 3, 1. But that's exactly the same as this vector 3, 1, which is like 3, 1 minus 0, 0. So these two are the same vector, even though they look different. They're the same because it's completely determined by this expression, endpoint minus start point in coordinates. And we'll see later that a vector is completely determined by two things, its direction, which we'll define, and its magnitude, which is like a length, which we will also define. So take a look. And the same thing works in R3 or in Rn, but just more difficult to draw. we'll see that any two vectors form some plane together, well, any two not parallel vectors, and we'll see that in section 5. Vectors in Rn come with a special kind of product that general matrices don't, and this is called the dot product. And this product tells us something about angle between vectors, which is really interesting. So it's very simple to define. You take two vectors, you multiply each of their components, u1 with v1, u2 with v2, and then you add them. So this is just like u1 v1 plus u2 v2 plus un vn. So it's very simple to compute. And we always write a dot for dot product. You don't write uv just next to them. And here's some properties. So u dot v is a real number. This is really important. If you if you dot two vectors in Rn, you get a real number, not a vector. By checking the definition, you could see that u dot v is v dot u, that if I dot the zero vector with u, then I get 0. Dot product is distributive, just like multiplication. And dot product is associative with constants, and you could also multiply constants inside the rightmost vector. And we could define the length using Pythagorean theorem, and we'll see how length and dot product are related. So the length or magnitude is just the square root of u dot itself, which should have a square root here. Sorry, that's a typo. So it's square root of u1 squared plus through un squared. And you can use this definition to see that the magnitude of Cu is absolute value C times U. That's not a dot product. That's a multiplication of real numbers. And if U is a non-zero vector, then U divided by magnitude U, which is the same thing as just the scalar, this one times the vector U, has magnitude 1. You can check that using algebra. This is called a unit vector, and this is very important in general. And we could check why this is just Pythagorean theorem using these ideas. So every vector is the hypotenuse of some right triangle. Here we have a base, here we have a height. This one has base vector 4, 0. This one has base 3, 0, 0, 3. And we know that 3 squared plus 4 squared is 5 squared, which is the length here. But that's defined to be the square root of 3 squared plus 4 squared, these components, 4 and 3 squared. And if you extend this to 3 dimensions, you could see that it'll still work. And then with induction, you could extend to n dimensions. We could define the angle between two non-zero vectors in the plane, non-zero because we want to divide by their magnitudes. So the magnitude is 0 if and only if the vector itself is 0. So this angle from 0 to pi is defined by the arc cosine of u dot v over magnitude u, magnitude v. In other words, u dot v is magnitude u, magnitude v, cosine theta. And theta is the interior angle. So if I have two vectors, the angle is this one. It's not the outside one. It's always the smaller of the two angles that these vectors make. And this angle makes sense because I could always consider these two vectors lying in the same plane, which we will see how they make a plane later on today. If u dot v is 0, we call the vectors orthogonal. And as a picture, they really do look like something like this if they are non-zero vectors. If any of them are 0, the dot product is, of course, 0 as well. So that's kind of an exception. Here's how this looks. If you have the vector u and a vector v, the third side could be interpreted as u minus v, because v plus u minus v gives u. And there's very many useful things you could do with vectors. A lot of geometry proofs are very simple with vectors, whereas otherwise they might be a little bit complicated. Um, so let's prove that theta really is this, considering these triangles in, say, 2 dimensions for now. So if the length of u is a, the length of v is b, and the length of u minus v is c, where a and b are not 0, by law of cosines, a squared plus b squared minus c squared over 2ab is cosine theta. And by the definition of magnitude, a is u1 squared plus u2 squared, and that's a squared, and b squared is v1 squared plus v2 squared. So c squared, we know must be this, just by, again, computing with components. And then a squared plus b squared minus c squared is this thing, which is 2u dot v. So you plug that up here, it's 2u dot v over 2 magnitude u magnitude v. And so theta is precisely what the theorem says. In general, you could define the angle between two vectors in Rn the same way, using the dot product and the magnitude, even though we can't picture or draw it. There are many reasons to see why this actually should be true, even in spaces we can't draw. So the following is a really important way to think about vectors. Let's define the direction of u to be this unit vector of u. Then u is magnitude times, this is a times, not a dot product, times direction. So every vector comes with a magnitude and a direction in this really nice way. So you could dot two unit vectors, and you could think of dotting two unit vectors as just cosine. Right? Since if we go up here, these will both be 1. So dotting two unit vectors just gives cosine. The 0 vector is the only exception. It has no direction. Its magnitude is 0. So based on figure 3, which is up here, we could talk about the distance between u and v. The distance should be the magnitude of u minus v. And that's how we'll define it. And you could prove the following. If we define distance this way, then the distance is always non-negative, and it's 0 if and only if v is u. The distance of uv is distance vu, and we have something called the triangle inequality. The distance of uv minus distance uw is less than or equal to distance uw plus distance wv. And you could do this by drawing points instead. So if I say this is u, this is v, this is w, then this vector is vw, this vector is uv, this is how we could denote these vectors. This is uw, and this is just saying that the magnitude of any of the sides, like this bottom side, is less than the sum of the other two magnitudes of the sides. So you can interpret this the triangle inequality as saying no side is longer than the sum of the other two sides. There's another important result that we won't talk about. It's called Cauchy-Schwarz. U dot v is less than or equal to magnitude u, magnitude v in general. So this is true, of course, if we take u dot v to be equal to magnitude u, magnitude v cosine theta. Cosine theta is less than or equal to 1. And so it balances out the magnitude u, magnitude v, and it equals u dot v. But here, if we just take absolute value and use inequalities, then this is true. So we know how to prove this based on the dot product. But you could also prove this not knowing anything about angles. So there's other proofs for this that don't rely on any kind of angle or cosine. Here's something else that's really interesting you could do with dot product. Projections. So define the projection of U onto V by this thing. And I will show you how I think about it later on. So here's a picture. We have a vector V, this one. We have a vector U, this one. And we have the projection, this one, which is just a shadow of U onto V. So we define the projection to be U dot V over magnitude V squared V, which is the same thing as U dot V over magnitude V, V over magnitude V, which gives it a direction and almost a magnitude. If U dot V is positive, so basically if these point in the same direction, just like in the picture, then this is a vector with magnitude U dot V over magnitude V, which is just U cosine theta by the dot product identity. And U cosine theta is just the side length of this side of the triangle. This is U cosine theta, and this one is U sine theta by geometry. So the length is U cosine theta. Actually, it's absolute value in general because it could be pointing out there in case V is going out this way. But the magnitude is absolute value of magnitude U cosine theta, and the direction is plus or minus V over magnitude V, depending on which way U and V are pointing. If they're pointing in the same direction, like here, then it'll be plus, and if V is going out there, if the angle is greater than 90 degrees, we will take minus. So that's why we define projection this way. So even if you had V out here and U is here, the projection is still going to look like something on this side. And the idea really is that we're not projecting just onto a vector. We take the line that is made by this vector and we project on the line. So really, this is kind of bad notation, and we should be talking about projecting onto a whole line instead of just a vector. And then it makes a little more sense what the magnitude and direction are. Yeah, so that's what this is. It's good to get practice with this. And we can also define the orthogonal projection, which is this other side, which we already said was magnitude U sine theta. Using vector algebra, this is just V minus the projection, because this thing plus projection equals U by definition of vector addition. So this plus this equals U. So it must be U minus projection. This is a typo. This should be U minus projection. Sorry. U minus projection. So the algebra works out. Here's what it says correctly. The projection plus this orthogonal projection equals U, not equals V. So that's a typo. And then we have another kind of Pythagorean theorem where the base squared plus the side squared equals the hypotenuse squared. Okay, so that's pretty much it for dot product. And then we could talk about cross product. In R3, there's another kind of product, and it's really special to R3. It's called the cross product. So first, let's talk about some notation. You let I be 1, 0, 0, J be 0, 1, 0, and K be 0, 0, 1. So you could remember what the cross product of two vectors are by taking the determinant of the following matrix. So it's not a real matrix because some components are actually vectors, but we still multiply them the same way. We take I times the minor here, and then we take, for example, J times this other minor here with a minus sign, etc. So you compute it just like a determinant. The actual definition you could take to be this one, but this is harder to remember than just one 3 by 3 determinant. So you should probably just remember the 3 by 3 determinant. And that's summarized with this definition here. If we write out the components, it gets a little complicated. Right? U2 V3 minus U3 V2 in the first component, and so on. So we always write a cross for cross product, and again, never UV or like U dot V. These are very different products. U cross V gives a vector, and let's summarize in general some properties. So U cross V gives you a vector in R3. You can check with the definition that cross product is anti-commutative, which means U cross V is minus V cross U. So this is interesting. Zero cross anything is zero. So that's a good property. Cross product is also distributive. Just remember to keep U on the same side that it was on. So if it was on the left, keep it on the left. It is also associative with scalars. It is not associative with cross product. U cross V cross W is not U cross V cross W in general, and you could check this by using vectors I, J, and K. Now, there's also a helpful circle, I, J, K. So if I cross I, J, I get K. And if I cross J with K, I get I. So it goes around in a circle in some nice way. And we've already seen this kind of diagram with determinants because determinants have something to do with permutations. So it's not surprising that we can remember this as some kind of circle or permutation. If I dot U with U cross V, and notice that this is not ambiguous at all, U dot U cross V wouldn't make any sense because this is a scalar and this is a vector. So U dot U cross V can only be interpreted one way, U dot U cross V. So we can write it without parentheses and it's not ambiguous. U dot U cross V is 0 and V dot U cross V is 0. U cross V is orthogonal to both U and V. So that's nice. You should watch some kind of YouTube videos about what cross product looks like depending on U and V. But basically, we have two vectors in space. We get a third vector that's orthogonal to both of them, which is a really nice kind of product. From 1 and 5, it follows that U cross any multiple of U is 0. And in general, U cross V is 0 if and only if U is a multiple of V or V is a multiple of U for some scalar C. And this is an interesting fact that you don't need to know or worry about here, but despite not having associativity, we can still work with something like U cross V cross W, even if we don't know what it is, because cross product satisfies some generalization of associativity called Jacobi identity. So if we take U cross V cross W plus V cross W cross U plus W cross U cross V, it equals 0. And we could use it by, if we don't know how to do V cross W, but somehow if we know W cross U and U cross V, then we could replace this left-hand side with the right-hand side. And I think that's really interesting. You could think of vectors lying in R2 by taking the third component to be 0. And that lets you cross vectors in R2 in some way. So it's interesting that if we think of it this way, U cross V, which is this scalar, is the area of the parallelogram with sides U and V. So this area is magnitude U cross V, which is also really interesting. And we could prove this. So the area of parallelogram is base times height. And so if we go down here, the base is magnitude U, and the height is, we already saw what this was. This side is V sine theta. So all we need to do now is show that magnitude U, magnitude V sine theta, is equal to magnitude of the cross product, which is another really cool identity. So cross product has something to do with sine, and dot product has something to do with cosine. So we know what theta is in terms of dot product. It's arc cosine of this thing. And you could plug in arc cosine t into sine squared plus cosine squared equals 1 and solve for sine of arc cosine to be square root 1 minus t squared. because this is just t squared. So sine theta is actually the square root of this thing. And then if you do all these computations, you get that the area squared is this magnitude squared, where the area originally was uv sine theta. So as a corollary, we get this very nice identity about the magnitude of cross product. And actually, you could define u cross v to be the vector pointing in some specific direction with this magnitude. That's another way to define cross product, and that's where we get the original formula with this motivation. In R3, you could also prove the following with a very similar method as the parallelogram. If I have a parallelepiped in R3, which just means it's a parallelogram base, and it's extended in R3 as like a three-dimensional kind of parallelogram, and this is u, v, and w, then the volume of this parallelogram, or parallelepiped, is the absolute value of u dot v cross w, which you can compute by doing this 3 by 3 determinant. And this product, u dot v cross w, is called the triple scalar product of u, v, and w. So that's it for dot and cross products. Let's talk about lines in space. And for this, you might want to reference Desmos and learn how to graph a little bit in Desmos because it can be a very powerful tool. And I'll give some examples here. So parametric equation of a line. This is a very important way to write a line in space. There's many types of equations, but this one is probably my favorite. So the way to write it is you start your line at a vector u. So here's my vector u. And then I start adding multiples of v to it. So this is like plus tv. And then I get this line, depending on the direction of v. So that's how parametric equations work, u plus tv for lines. And if I restrict my domain to specific values like -10 and 10, I get what's called a line segment. So for example, here is a line segment in Desmos. U plus tv, my u was 2 minus 1, 3, and my v was 1, 1, 2. So this is 2 minus 1, 3, plus t, 1, 1, 2. So this is like u and this is v. This direction is like the direction of 1, 1, 2. And I restricted my domain to -2 to 0, and I get a line segment. It stops here, and it stops here, so I just get a piece of a line if I don't let my domain be all real numbers. And you could take a look at the description of that figure. You could think of this as kind of a point slope formula. You have a point u that is contained on the line, and it goes in the direction of v. And a line really just needs two pieces of information, as you are familiar with in geometry. 2 points determine a line. So here, 2 points u plus u and some multiple of v added together determine the line. You could also write this out completely by writing out the coordinates, like x is a1 plus b1t, y is a2 plus b2t, t is a3 plus b3t. So in figure 5, this line that I drew, the line segment, it satisfied x minus 3 is y and 2y plus 5 is z, if you play around with it a little bit. So you could solve for y. Y is x minus 3 is z minus 5 over 2. In general, you have the Cartesian form of a line containing 2 points. If you know 2 points on your line, you could also write it as this set of equations. So these are equal, and these are equal. And that gives you a line. And this again can also be generalized to Rn. Yeah. So we talked about orthogonal vectors, but we can also define two vectors to be parallel if v is cv prime for some non-zero scalar c. And then we could talk about lines being parallel. U plus TV and U prime plus TV prime are called parallel if V and V prime are parallel. And they intersect if there are T0 and T0 prime, not necessarily the same. This should be T1, not T0 prime. So T0 and T1, such that these two are equal. And the lines are called skew if V is not parallel to V prime and the lines don't intersect. So in R2, there are no skew lines because two lines are either parallel or intersect, or both. They could be the same line. So for example, let's consider these two lines. So 2, 2 minus 1 plus T, 3, 1 minus 3. And this other line, 1, 0, 1 plus S, 6 minus 4, 9. We should use different parameters, T and S, to not get confused. The graphs of these lines are independent of the parameters. We just care about the graphs and whether the graphs intersect. Therefore, intersecting also does not depend on these parameters. The two lines are not parallel because this direction is not a multiple of this other direction. You could prove that if C existed, it must be a half because of the first coordinate. But then minus 4 times a half is not 1. So C does not exist. Do the lines intersect? To do that, you have to set them equal with the different parameters, and you get a system of 3 equations with 2 unknowns. From the first equation, you could find that T is minus 8 over 9, and S is minus 5/18. That's just if you solve these two. So now you could plug it into here and see if it is satisfied. It's not. So this side will not equal, the left side will not equal the right side, and so there's no solution to these two lines being equal. If there was a solution, then they would intersect precisely when T is minus 8/9 and S is minus 5/18. But it's not. So they don't intersect, they're not parallel. These are skew lines. Now let's talk a little bit about planes. Planes also have a parametric form. So imagine a plane passing through the origin. Vectors in the plane are all linear combinations of just two vectors. So for example, in the xy plane, I could look at two vectors, this E1 and E2, or we call them J and I as well before. So here, if I take any point, it's going to be some multiple of E1 plus some other multiple of E2. And I could do that for any point. It's some multiple of E1 plus some multiple of E2. And this is true in general. If I have an arbitrary plane anywhere, as long as it passes through the origin, I could write it as a linear combination going through all T and S of some vector V and some vector W. Now, if it doesn't pass through the origin, I just need to shift it by some vector U. So in general, and sorry, this is a typo again, should be ST. R of ST, which is like a parametric equation for a plane, in this case, is given by some vector plus TV plus SW. And just like in 2 dimensions, a slope and a point determine a line. In 3 dimensions, a perpendicular vector to the plane and some point on the plane completely determine the plane. So we also need 2 pieces of information somehow to get a plane in R3. In higher dimensions, this is not the case. We'll be focusing mostly on 3 dimensions in the rest of this lecture. So 3 non-collinear points, so not lying on a line, we could call them PQR, and we can make 2 vectors out of them. This one is called PQ vector, and this one is called PR vector. So we have these 2 vectors. We can actually describe this plane by computing the cross product, and then we call this the normal vector n. So compute n is PQ cross PR to get a normal vector. And then you know a point on the plane. The point is P. So if we shift all the points of this plane to the origin, so x, y, z minus P, and then we dot with the normal vector, we should get 0 because all of these vectors in the plane are going to be orthogonal to this normal vector. And that's the idea. So the kind of point slope formula, it's actually called, I guess, point normal form, is this equation. So normal vector dot xyz minus a point is 0. We will be rewriting it in a few different ways. So this is like n dot xyz minus n dot p is 0. And you can check that what point you pick doesn't actually matter for this equation, even though it looks like it does depend on the point p. So you could try to figure out why it doesn't depend on a point p on the plane. If p is x naught, y naught, z naught, then this is written this way. Or sometimes the constants, these constants are absorbed into D, and we just take n to be ABC and write the equation of the plane as ax plus by plus cz plus d. And here d is this minus n dot p. So here is a way to write a parametric equation for a plane in Desmos. You need to use u and v as your parameters, or else it won't work. It won't let you set the bounds for the parameters unless you make them u and v. So here, 0, 0, 5 is a point on the plane. This is the parametric equation form. So 0, 0, 5 is a point on the plane. And I just see that this vector lies in the plane. Anything from 0, 0, 5 to anywhere else, any other point on the plane is a vector lying in the plane. So if this is P and this is Q, PQ is orthogonal to N. Or if this is R, then PR is orthogonal to N. You could also write it a slightly different way, which is sometimes helpful. So if a plane contains the non-zero points, x naught 0, 0, 0, y naught 0, and 0, 0, z naught, and the picture is, here's the x-axis, y-axis, and z-axis. The plane intersects here, here, and here somehow, and goes on forever in the other directions. You could figure out how to write this plane just by knowing where it intersects the axes. And to do it, you just write this, which also works in 2 dimensions. So if I have a line and it intersects at 5, and here it intersects at 3, then I can very quickly write the line down as x over 3 plus y over 5 equals 1, which is sometimes helpful. So you don't need to compute the slope. You don't need to divide anything. You don't need to subtract anything. You just use the x and y intercepts, which most lines have. If a line passes through the origin, then that's a problem. But if it doesn't pass through the origin, then it'll work. Well, I guess, or if it's not parallel to one of the axes, then it won't work either. Let's talk about distances of points, lines, and planes. We already discussed what a distance between 2 points look like. Let's talk about how to find distance from a point to a line. So the idea is that this line here is u plus tv. So here's my vector u, it's coming from the origin somewhere, and here's u plus v coming from the origin somewhere. Then this vector is the vector up. And then we could set up this triangle. If we have a line and I have a point, the distance is given by the magnitude of this vector the orthogonal projection of UP onto V. And I know how to compute all that. And I also know that this is equal to UP sine theta. And I had an identity for cross product involving this. So this is equal to UP cross V over magnitude V. Because that's the angle here. If this vector is V and this vector is UP, then that's how I got sine theta between the two vectors. So that's all. The formula is very simple and it's relatively simple to derive. It's just UP cross V over magnitude V is the distance. So let's see an example. So let's say I have a point 0, 2, 0 and a line 1 plus 3t, 2 minus t, 1 plus 5t. That's its parameterization. So we need to figure out UP. Here u is 1, 2, 1. So p minus u is UP. It's 0, 2, 0, minus 1, 2, 1, which is minus 1, 0, minus 1. And a vector v, which is, well, our line is given by u plus tb. So we just find what v is when we look at our line. So we can rewrite it as 1, 2, 1 plus t, 3 minus 1, 5. And so this is v, and this is u. So v is 3 minus 1, 5. And then I cross them. The order you cross them won't matter because you're taking an absolute value in the end. But for cross product, the order does matter. So crossing UP with V, I write UP first and then V second, and I do this determinant, and I get minus 1, 2, 1. So the magnitude is minus 1 squared plus 2 squared plus 1 squared. Which is root 6, and V magnitude is 3 squared plus minus 1 squared plus 5 squared, which is square root 35. So the distance between P and this line R of T is UP cross V over magnitude V, well, the magnitude of UP cross V. So notice this distance really makes sense because if I have a point, the distance between the point and the line is just the shortest distance. So it should be whatever this is that makes a right angle with the line, which happens to be an orthogonal projection of something very nice that we can easily describe. So that's it. What about distance between point and plane? So the picture is somewhat similar to the distance between point to line. So we take a point P in space and a plane in point normal form. Usually we work with point normal form for all of these things. Take any point U that lies on the plane. So you can usually compute this by choosing yz to be 0 or xy to be 0 or something along those lines. And you can project UP onto the normal vector n. So the picture is something like this. Here's n, here's p, here is UP. We just start n at wherever u starts. So we think of n as coming out of there. And then you project onto n. So you project, and it should give you the exact height directly above the plane. That's the picture. So it'll have something to do with projecting UP onto n. And that is all it is, actually. So the projection of UP onto n. And you can rewrite it in a few different ways that are convenient. So distance from point to line was a cross product. Here we can write it as a dot product, slightly different. Or we could write it like this. And this is interesting because the top is just the equation of the plane. But instead of plugging in x, y, z, we plugged in the point P, which is not necessarily on the plane. If it is on the plane, then this satisfies equals 0, and the distance is 0. Otherwise, if it's not on the plane, it won't be 0. So you could take a look at the notes for how to prove this and the ideas behind it. And so it's very easy to compute as long as you have a formula. So if I have a plane like x plus 2y minus 3z is 1, and a point like 1, 2, 3, I just plug in my a, b, c, and I plug in my point 1, 2, 3, and I plug in my normal vector down here, find the magnitude, and I get 5 over root 14. So this is very simple without the discussion above proposition 95. Like you don't need to remember how it's derived anymore in order to use it. You just use it if you need it. And if you ever forget what the formula is, you could rederive it yourself. Um, you could also figure out what the point is that's closest to P. It's going to be P plus some multiple of N. So P lies here. And if I add some multiple of N, then I'm going straight down. I just need to figure out what this multiple is. And the idea is that you take the distance of P, so the distance should be 5 over root 14. And if I add some unit vector in this direction, I will arrive at the plane. In this case, to make a unit vector, I need to divide by root 14. And the 5/14 accounts for the length. So again, you could take a look at the notes for how to derive something like this. In this case, the point on the plane closest to P, which is a different problem than just finding the distance, is this point here. And you can check that it really does lie on the plane by plugging it into the plane formula, x plus 2y minus 3z, and getting 1. And here is what this picture looks like. So my red vector is UP. My point on the plane is this point, which is the closest point to the green point 1, 2, 3. So that's the picture it makes in Desmos. But for now, let's talk about the distance between a line and a plane. So this is very simple. If your line is given by a parametric equation, then you could check whether the line intersects the plane just by plugging it into the plane. And if I plug it into the plane, then this tells me whether there's a solution to the line intersecting the plane, right? If this equals 0, then there's a solution. So we plug it in, and you could solve for t. So t is minus d plus n dot u over n dot v if you solve for everything above with the u1, u2, u3, v1, v2, v3. This is assuming n dot v is not 0. That is, the vector in the direction of the line, v, is not orthogonal to the normal vector, n, of the plane, which would mean that the line passes directly above or below the plane, or somehow it just doesn't intersect the plane. Or if it lies in the plane, then that's also a possibility. In that case, we still get a solution. We can't use this formula because we can't divide by n dot v. But if n dot u plus d is 0, then that means u is a point on the plane, which means that now the whole line is on the plane because the direction v lies on the plane. So if the line does not lie on the plane, you could just plug in, if it doesn't lie on the plane, then it must be parallel to the plane in some way. And in that case, you could plug in any point because every point is directly above some point on the plane in an orthogonal way. So in particular, we could plug in u into the formula above. And for example, we can compute n dot u plus d over magnitude n, where our line was u plus tv, and our plane was n dot xyz plus d equals 0. So that's how to find the distance between a plane and a line. Now we can talk about distance between two lines, which is a little bit trickier. If the lines are parallel, we can compute the distance using the same formula as point to plane, because every point of the first line is equidistant to the second line. Oh, sorry, point to line, not plane. Right? In this case, you have two parallel lines, and you pick any point to find the distance to the other line. You just use the point to line formula. If the lines are not parallel, then this cross product of their directions is not zero, right? By definition. The cross product is zero if and only if these vectors are parallel. So it's not zero, and we can transform one of the lines into a whole plane, and then we can compute the distance from the top line to the plane. So how do we do this? We take these two lines that are not parallel and don't intersect, and we take the cross product of their directions, and we get a normal vector. So take the normal vector and think of it as starting from the line, and then make a plane containing that line. So to do that, you just take this normal vector and you take the line ax plus by plus cz minus n dot u, because n dot u, or because u prime is a point contained in that plane. U prime is here. And then since n dot v prime is 0, we know that u prime plus sv prime is contained in the plane for all s, because you could just compute it. If I take this dot product, I distribute the dot product, n dot v prime is 0, and then I get n dot u prime minus n dot u prime is 0. And this is a u prime. So this really is the equation of the plane containing the whole line u prime plus sv prime. And now you could just use the line to plane formula, which was, again, just some projection of something. Sorry, not line to plane, just point to plane, because this line lies directly above the plane. Well, yeah, line to plane, point to plane, it was the same thing in this case. So we just plug in u and u prime, which you could write many different ways. One of the ways being this way, as long as you know which one is u prime and which one is v prime. So this is the plane containing u prime plus sv prime. In that case, you plug in u into the formula. And that's it for distances. I think I should also talk about two planes intersecting. So if I think about x plus 2y minus z equals 2, and I don't know, x plus y plus z equals 2, then two planes actually intersect in a line. So how do I figure out what line it is? There's a lot of different ways. You could use the Cartesian form of the line. So if I add the two equations, I get something like 2x plus 3y equals 4. So I get x equals 4 minus 3y over 2. What about z? So for z, I could just plug it into the second equation and get something like 4 minus 3y over 2 plus y plus z equals 2. And I could solve for y in terms of z. So I get like 4 minus 3y plus 2y plus 2z equals 4. The 4's cancel, and I get 2z equals y. So this will equal to 4 minus 6z over 2. And now I have an equation in this Cartesian form, equation of a line. What I could do from an equation like this in order to get to parametric form is I could set these equal to t. And that's a really nice way to get an equation of a line. So if I set this equal to t, then I get x equals t, 4 minus 3y over 2 equals t, and therefore 3y equals 4 minus 2t, and y equals 4 minus 2t over 3. And finally, since I already solved, I erased what z was, so I'll have to start over. 4 minus 6z over 2 is t. So I get 6z is 4 minus 2t. So z is 2 minus t over 3. So I get my equation of the line. It's t 4/3 minus 2/3 t and 2/3 minus 1/3 t, which I can rewrite as u plus tv. I can rewrite it as 0 4/3 2/3 plus t times 1 minus 2/3 minus 1/3. So if I have two planes, I could figure out their intersection, which is usually a line if the planes are not parallel. And I could figure out what the parametric equation for that is.